Hi everyone, welcome to Deep Learning Talks by Puru. Today's topic is going to be around logistic regression. We have talked about logistic regression a couple of times, but it's never enough. It is one of the fundamental learnable algorithm for classification. One of the first algorithms that I ever studied, and I think people generally study. So we are evolving our thought process from linear regression to logistic regression. So in the last video, we discussed something around linear regression. We saw the equation y equals to mx plus c, where m and c are the parameters, and y is basically the predicted value, and x acts as our input. Now, why do we need logistic regression once we already have a linear model like linear regression? To first answer this question, let us first try to understand what is it that we're building. We want a classification solver, a classification predictor, an algorithm that can help us classify. Let's start with something where the algorithm helps us classify whether this is a pen or not, whether this email is spam or not, should I buy this house or not. All binary classes. We only have two decisions, 1 or 0, right? Let's call them class 1 or class 0. We want the ability to answer these kind of questions. Now, linear regression, the output y is always unbounded. It ranges from negative infinity to positive infinity. The output of a classification problem is always bounded. It's always discrete. We always have countable number of classes. Here in our case, we have only two classes. Let's call them binary classification. So, is linear regression compatible for doing binary classification? Not really. Although it's a linear model, but not really. The output is unbounded, the output is continuous, the output is not discrete, right? Now, the second reason is the linear regression model is completely linear, right? The data might be non-linear, right? But the model is completely linear. Exhibit or we might want to exhibit some sort of complexity in our data, some sort of non-linearity in our data using our model. But linear regression is incapable of doing that, right? So largely we want to evolve linear regression into such a way that we are able to do binary classification. What all do we need to change? This is the main answer. What all do we need to change? One thing that we need to change is that what if we could modify the output negative infinity to positive infinity to evolve as probabilities, right? What probability? Probability that given this data point, it belongs to class 1, right? Given this data point, it belongs to class 0, right? What if we could evolve the output y to probabilities, right? Now, the second thing is, what if instead of computing sum of squared errors, what if we could produce something like a decision boundary? So this is what we want ideally from linear regression. We want to push linear regression and evolve linear regression to be able to solve these kind of problems. It should become a probability estimator for us, and it should be able to produce a decision boundary for us. Yeah. So I think these are the two things that we should first aim to solve with linear regression. To solve probabilities, since we know that logistic regression is going to be a probability based model, it's going to be a probability estimator. To solve probabilities, we have something known as an activation function. Now, this activation function that we use in this case is known as a sigmoid, sigmoid, sigmoid activation function. So what intuitively it does is it squishes all the output of linear regression that ranges from negative infinity to positive infinity. It squishes them between 0 to 1. It helps you approximate the probability of the class 1 for this particular data point, right? So it's a very good probability estimator. It's a very good projection of negative infinity to positive infinity between 0 to 1, right? So it's an activation function. So you don't have to think about activation functions as some other special mathematical functions. It's a simple activation function that is nonlinear. The function is known as 1 upon 1 plus e to the power minus x, where x is the input of sigmoid, and whatever you give to the sigmoid function, it squishes it between 0 to 1. So large positive values will tend to move towards 1. Large negative values will tend to move towards 0, and it is centered at 0. So 0 is going to produce the probability 0.5, which can act as your threshold. Now, the training of any algorithm like logistic regression should be smooth, and we know that in the training we're going to be differentiating the cost function, and the cost function is going to contain some component of sigmoid, so it should always be differentiable, right? So it is smooth, it is differentiable, and it also does non-linear transformations. It basically adds in non-linearity, right? Since it's a nonlinear activation function, it increases the degree of polynomial of our equation to more than one, right? It also adds the flavor of nonlinearity. So now the fundamentals of logistic regression are in place. We know that we need to evolve from linear regression to logistic regression. Although the name suggests logistic regression, but it's a classification problem, right? It helps us predict classification based outputs. It helps us solve classification problem. Logistic here correlates to sigmoid or logits or probabilities. So probabilistic regression, I think maybe we can think of it like that. So, what is the intuition behind logistic regression? So, logistic regression, think of it in terms of probability. What is the probability that this person X or this person will buy a house given the age and income of this person, right? So, it's a conditional probability model, right? So, think of logistic regression with respect to probabilities. Now, the loss function or the cost function that we were using in case of linear regression was known as sum of squared residuals or sum of squared errors. Here we want that function also to evolve. We don't want to continue with that function, because if we use that function here along with sigmoid and with the probability model, we will not be able to put in the pieces, and the function, the large function will get non-convex. It's not going to be a convex function, and it might have multiple local minima. We might not be able to converge using gradient descent. So we want something like a likelihood function, something like a probabilistic function that can help us approximate probabilities. So we use a function known as maximum likelihood estimation. Maximum likelihood estimation helps us find the best parameters given the data, right? So it helps us figure out what are the best parameters given the observed data, and what are the most likely parameters given this particular observed data point X, right? So what we generally do is we figure out the maximum likelihood estimation function, then we take the log of that maximum likelihood estimation function. Then we take the negative log so that we find the negative log likelihood. Why do we take the negative log? Because all our optimization algorithms in PyTorch and in sklearn are trained or are basically are written in such a way that they perform negative optimization better, right? So once again, maximum likelihood estimation is going to be our main function in logistic regression. So in linear regression, sum of squared errors worked really well, right? Because we were directly dealing with the true and the predictive and predicted variables, and we were trying to find the distances between true and predicted values, right? But in case of logistic regression, we're always predicting probabilities, and the probabilities are always between 0 and 1. So if we use sum of squared errors here, it would create a non-convex optimization problem. If we have a non-convex optimization problem, then I mean we might not be able to find the best local global minima. We might not be able to find the best global minima. We might have multiple local minima, and with multiple local minimas we might not be able to converge very well. We might not be able to guarantee that we are at the global minima and these are the best parameters, right? We might not be able to converge, right? So there are a lot of nuances with respect to calculus that might help us you know not perform the best with sum of squared errors being the loss function for logistic regression, and we need a probabilistic based loss function, meaning a likelihood based loss function. So that's why we use something known as the maximum likelihood estimation. So how do we arrive at maximum likelihood estimation? We always think about probability of a single data point, let's say I, probability of yi given xi. So given this particular data point, given the information about this particular person, I want to find out the probability that this person belongs to class 1, right? So this is basically conditional probability. So we try to write the conditional probability formula for a single class, then for the next class. Then we try to generalize for the probability formula for both the classes, right? So which is probability of yi given xi, and then that likelihood model we extend to the whole data set. Right now we were dealing with yi, a single I. We extend it to the whole data set by using the product of all the probabilities across the whole data set, and then that is what we get as the likelihood function. So likelihood function for the whole data set, then we take the log of that particular likelihood function, and then we negate that log to convert it into negative log likelihood function. Though, so that negative log likelihood function comes from a simple probability model. The negative log likelihood function evolves into a cross entropy loss. It is also known as binary cross entropy loss. If we extend it to multiple classes to solve k-set classification problem, it becomes a generic cross entropy loss. Okay. So now you have the loss function. Now you have the probability model. You have a probability estimator. How do you figure out the best parameter, right? How do you find out the best parameters? So now that we talked about sigmoid being differentiable, binary cross entropy loss which is the negative log likelihood function, also being differentiable, also being convex. So that means it has a global minima. Why don't we use calculus? Why don't we use the same fundamental principles of gradient descent? What does the fundamental principle of gradient descent say? They simply say that differentiate the loss function with respect to all the parameters, parameter p1, p2, p3, theta 1, theta 2, theta 3, and so on, and keep on updating them. So let's say I have 1000 iterations to run. For the first iteration, starting my loop from first iteration till 1000, I will keep on differentiating or finding the partial derivative of my cost function. What is the cost function here? Not sum of squared residuals. The cost function here is the negative log likelihood function, right? I will try to figure out the partial derivative of the negative log likelihood function with respect to my parameter theta. And then I will update my parameter set theta, right? How will I update? The new theta is equal to the old theta minus learning rate multiplied by the partial derivative of cost function with respect to theta. That's it. I will keep on doing this. I will keep on differentiating and updating, differentiating and updating, differentiating and updating for all 1000 iterations, right? To converge to my most optimal parameters. Here, what is the number of iterations? It's kind of a hyperparameter. We control it. We as engineers, as data scientists, as applied scientists control what is going to be the number of iterations. What is the learning rate? We are going to control the learning rate. Learning rate basically is the step size, the amount of steps, or so the amount you want to update, or you want to quantify how much gradient do I want to update. So that is basically the step size. So learning rate helps you take step down towards the minima. So the more the learning rate, the bigger is going to be the step size, right? So you want to take a nominal step size. You don't want to take a very large step size, because if you take a very large step size, let's say you take your learning rate as 1000, right? There might be a possibility that you might overshoot from your global minima. So let's say this is how you are approaching your global minima, right? Slowly. And if you take the step size as very large, you might overshoot your global minima. So if you want to visualize what really happens in a linear regression, you start with a random line and you fit the best fitted line on your particular data set. If you try to plot it on a two-dimensional axis plane, you will be able to see it very nicely. Now, what about linear regression? Oh, sorry, what about logistic regression? If you want to visualize what is happening in logistic regression, you start with a random decision boundary at a random place. There are two classes, class 1 and class 2. Data points of class 1, data points of class 2, right? Let's say they are on the lower triangular part and the class 2 is on the upper triangular part. Your decision boundary is scattered randomly. Now, as soon as you click the training methodology, or as soon as you click the training part, your decision boundary will start reaching to an optimal place such that it separates class 1 and class 2 nicely, right? This is what happens during the training. And your decision boundary or the best parameters are being what you call approximated while training. Now, when do you use logistic regression? Let's say you are dealing with a small to medium sized data set and you're solving a binary classification problem. The complexity of your data set and the complexity of the problem is not high, because largely the model is linear. We are producing linear decision boundaries and you want very high interpretability, right? You should use logistic regression. And you want the training time to be very, very fast. You should use logistic regression. You want least risk of overfitting. You should use logistic regression. And you want a probabilistic output. You should use logistic regression. So if you are dealing with a very large and very complex data set and you can afford to have GPUs, you can afford to have higher training time, use neural network in case of logistic regression. If you want more and more complexity, if you want the ability to exhibit more and more complexity in the data, and you want your model to be highly nonlinear, then use neural network over logistic regression, right?